right, so today what we're going to look at is the algebra of stats, and this you know already. We talked about it briefly, but we're going to hit some of the high points. There's two ways that we can look at stats. We can look at discrete values, like a dice rolling a 1, 2, 3, 4, 5, 6, or we can look at continuous variables like if you're looking at somebody being in a location. They could be a meter, they can be 2 meters, whatever. Missing. So if you do the continuous variable, so discrete are individual numbers like whole numbers, 1, 2, 3, usually positive values. And when we look at distributions, what do all probabilities have to add up to for a discrete? They all add up to 1, right? Now, when we look at continuous, what is the area from negative infinity to infinity of those probabilities? What do they have to add up to? They have to add up to 1. So that's a great place to start. So discrete, the probabilities add up to 1. Continuous, the areas add up to 1. And we kind of know that already. Now, when we get to expected value, that's like the mean, but not exactly. Expected value is, let's say we had the basic one. Let's say you had, you rolled a 1, 2, or 3, and the probability of rolling a 1 was, probability of rolling a 1 was a 1/6. The probability of rolling a 2 was a 3/6, and probability of rolling a 3, what would it have to be? 2/6, right? Or 1/3, yeah, because they have to add up to 1. Now, the expected value for that is you're going to take 1 times 1/6 plus 2 times 3/6 plus 3 times 2/6. You just set that down, thanks. And will this add up to 1? No. No. And think of our games that we played when we had some winning and losing. Those expected values have to be less than 0 if the house wants to win. It should be greater than 0 if you want to win, right? So this is going to be 1/6 plus 6/6 plus 6/6, which is going to be 2 1/6, right? Or 13/6, not equal to 1. So that's the first thing I wanted to remind you of, is that when we do expected value, it is xi times the probability of x. They go x equal to x. And you add all those up, and those are going to be what they call your expected value, e of x. Okay, if you're doing a continuous, since this is x, what are we doing to our probabilities? We're multiplying them by what? X. So wouldn't the expected value for a continuous just be negative infinity to infinity of x times p of x? Boom, done. That's all there is to it. So that's expected value for figuring those out. So those are some things that we've talked about and just reinforced a little bit. Now comes the transformation part. So we're going to go back to expected value. What's the expected value of a constant like D going to be? Like if every time you roll a die, it turns up 5. What's the expected value? 5, right? So that's going to be D. Now the expected value of some constant times x, all right, so you can kind of see they're going to go all out. They're going to go cx plus d. They're going to do the whole linear transformation here. What you do here is you have e of cx plus d. That's the sum of cx plus d times the probability. This is what we're putting in for x. Instead of x, we're putting cx plus d times p. So it'll be cxi p plus dpi. Well, what do all the probabilities of a constant add up to? 1, right? So this is d times 1, which is just d. And then this one is just going to be xpi, or the expected value, times c. So when you see a e of cx plus d, you're going to pull the c out in front of the expected value and then add the d. And what's cool is if this book does a nice job of proving everything to almost a fault. If you integrate this, cx plus d times f of x, you're going to get c times x f of x dx plus d times the integral. Well, for d, this integral is going to add up to 1 for the constant. So therefore, it's going to be d times 1, which is d, and then it's c times the definition of e of x. So it works out c e of x like that. All right, and then we get to, so that part's okay? Sure, sure. This part? This one? Yes. Yep. So this is the full expected transformation c x plus d. That's going to be equal to c times e of x plus d. A little weird, but hopefully makes sense. They have a nice example there. Then the last part is the variance. Hold your fingers like this. The expected value is kind of like our mean, where you expect things to line up. The variance is how far they're apart. That center is. So the center is in between, but how far they spread, that's your variance. Variance is sigma squared. So what's the standard deviation of that? Yeah. So that's just the square root of that squared. So just remember that you sometimes have to do that. Now, by definition, it's the expected value of x minus mu. Every x you have minus mu squared is going to be your variance. And so to show that, what that's equal to, we go e of x minus mu squared. You square those out, FOIL it. You'll get e of x squared. You'll get e of mu squared. You'll get e of 2 mu x. Well, e of x is just e of x. 2 mu is a simple constant. And then the expected value of mu squared is mu squared. We don't know what e of x squared is. But if e of x is mu, we have negative 2 mu squared plus mu squared. What is negative 2 mu squared plus mu squared? What's that? Negative mu squared. So therefore, this can be the e of x, which is mu, quantity squared. So whenever we look at variance, I think we talked about this, didn't we? It's the expected value of x squared minus e of x quantity squared. Now look at what happens with the continuous. Watch this carefully. The variance of x is going to go from negative infinity to infinity. This e of x squared, well, we said that the expected value was from negative infinity to infinity of x p of x, right? Remember that? That's what that one is, squared. What do you think this one is, e of x squared, as an integral? Something p of x dx, what do you think it is? It's just x squared. This is x squared p of x. This is x p of x. See kind of how it's starting to fit together a little bit? For a continuous, you would go x p of x in the integral for expected value. E of x squared makes sense. It's just x squared p of x. And what was this one again? P of x from negative infinity to infinity. What was that? That was 1. This, not 1. And this won't be 1 either. But the difference is your variance. And what do you need for standard deviation? You got to do the square root of that. All right. Then the last thing I just want to show you is the variance transformation. I love it. Okay, hold your fingers like this. Now spread. So if we move this over D, does that spread change? No. No. So what do you think the variance is of D? 0. It doesn't change. So the variance is 0, and the variance of cx plus d is going to be this annoying c squared variance. And the reason it becomes that, you can see this proof is pretty simple. The variance of cx plus d, when you do the cx plus d squared minus cx plus d e quantity squared, all the algebra gets things to cancel out, and the d squareds will cancel. You'll get c squared e of x squared minus c squared e of x squared, and pull out the c squared, you get c squared e of x squared minus e of x quantity squared. That just is the what? What is that? That's just your variance. So it's c squared times the variance of x. So what are we doing here? Well, if you look at e of x, cx plus d, cx plus d, that's just going to be c e of x plus d. If you do the variance of cx plus d, the d is nothing, but the c is going to be squared of variance of x. So those are the two that we're working with, and I think we actually did those before. And then if we do a combination of things, we add more to each other. What happens with that is that the expected value is just the sum of those, and the variance is also the sum. So it's a little hard to see here, but the expected value is the sum, and the variance is the sum. And we'll go over that in just a little bit. So let's do this example 7. This is all I need to do. The random variable x is a distribution of mu equal to 11 and a standard deviation of 2. Define 3 independent variables, x1, x2, and x3, and you're going to find the mean or the expected value of these 3 and the variance of those 3. So if we do e of x 1 plus 2 plus 3, we can split them up. E of x1 plus e of x2 plus e of x3. Likewise, variances. Variance x1, variance x2, variance x3. But what you have to do, though, is you have to see, okay, for this 2x, that's going to be 2e of x. It's going to be 4 variance of x. For this 4 minus 3x, it's just going to be 4 minus 3e of x. It's going to be 0 plus 9. And not negative. We never have negatives here because it's squared. 9 variance of x. And then you'll have, for the expected value of e x3, 4e of x plus 1, just 16 variance. So when you add those up, you get 29 variance, or 29 times 2 squared, and which is 116. This one you get 3 times 11, 3 mu plus 5. 3 times 11 plus 5 is 38. Am I going a little fast, or is this okay? So this is the overview of the formulas from this, the expected value and variance transformation and sum, and then the definition of variance, e of x squared minus e of x quantity squared. All right, so there you go. So what we're going to do is you're going to do these problems. Answers are at the end.